All right, so here's assignment 7.5. Let's start with number 1. So you're given a tricky function, 1 over e to the x, transcendental, fancy name. And can I make a Maclaurin polynomial out of it? What would be the steps I would do? So you're given a function. Maclaurin means you're going to plug in 0. So I have a function, I'm going to plug in 0. E to the 0 is 1, so 1 divided by 1. That's our start. Then we're going to take the derivative. Now 1 over e to the x. I want to see this in calculus-friendly terms as e to the negative x. So when I take the derivative of e to the negative x, there's a hook and it's negative. Then when I plug in 0, e to the 0, I know the camera's going crazy. E to the 0 is 1, but it makes it negative 1. When I do the second derivative, it's e to the negative x, and a negative times a negative makes it positive. Plug in 0, and you can see there's a pattern happening here where it's going to alternate. So take the derivative again, plug in 0, take the derivative to the 4th, because that's what it said. And you can see it alternates between positive 1 and negative 1. And then we're going to take those values and create a new polynomial out of it. And so how do I do that? So f at 0 equals 1. We start there. Then I have negative 1, and it's x minus 0, which is just x, to the exponent 1 over 1 factorial. Then I use the next number, plus 1. X to the 2 over 2 factorial. Oops, next it's negative. That's x to the 3 over 3 factorial plus x to the 4 over 4 factorial, and so on. Number 2. Use the problem from 1 to approximate 1 over the square root of e. Well, 1 over the square root of e would mean that x would equal 1/2, because if e to the 1/2 means the square root. And so I would plug 1/2 in for x. So 1/2 divided by 1, we have 1/2 squared divided by 2. We have 1/2 cubed divided by 3 factorial, and we have 1/2 to the 4th divided by 4 factorial. And then you'd use your calculator to do it. And I'll do it for you. The answer is about 0.60677. Number 3. Use the definition of a 4th degree Maclaurin for f at x equals e to the 3x. So Maclaurin means we're going to use 0, which is wonderful. So e to the 0 is 1. Then I take the derivative, that's e to the 3x with the hook. Again, I'm going to plug in 0, so that's 1 times 3, which is 3. Take the second derivative, again we're going to do this to the 4th degree. That's e to the 3x with the hook, that's going to be 9. Oops, this should be derivative, second derivative, up here too. This should say derivative, second, third, and 4th. All right, the third derivative, e to the 3x, and then the hook times 9 is 27. That's 3. And then the 4th, 27 times 3. What is that? 60 and 21, so 81. All right, so those are the values we're going to use. And now the pattern. So f at 0 equals 1. They're all positive, so plus. Then I start with 3. Because it's Maclaurin, I don't need to go x subtract 0. I can just go x to the exponent 1 over 1 factorial. Then the next number is what? 9. It's x to the 2 over 2 factorial. Next one's 27. and the next one's 81. And you did it. And that's called a Maclaurin expansion, polynomial expansion. Number 4. Use the definition of a fifth degree. So we have g at x equaling x times e to the x. Again, we're going to plug in 0. So if I plug in 0, the answer is 0. You might think it would be that way every time, but we got to do the product rule. The first times the derivative of the second plus the second times the derivative of the first. So when I plug in 0 here, it is 0 at the beginning. But e to the 0 is 1, so it's not always going to be that way. The next derivative, again, the power rule, with the product rule, the first times the derivative of the second plus the second, and then e to the x is e to the x. There's going to be a pattern here. And so this answer is going to be 2. I bet you know what the next answer is going to be, and so on, if you just follow the pattern along here. So for the next one, the product rule, the first times the derivative of the second plus the second, and then we're just going to keep, see the pattern. It's going to another e to the x, which is what makes this 3. And once you see the pattern, it's okay. And you're doing it to the fifth. So I see the pattern. There it is. Then, how do I write this as a polynomial? So I start with 0 plus, they're all positive. Then it's 1. And because it's Maclaurin, it's just x to the 1 over 1 factorial. X squared. Oh, sorry, the next number I start with is 2. And then x squared over 2 factorial. Then I start with 3. X cubed over 3 factorial. 4. And 5. And it's done. Number 5. Use the definition of a third degree for c equals 1. So I'm going to write this as x to the 1/3, and we're starting with 1. So it's a Taylor, not a Maclaurin then. 1 to any exponent is equal to 1. And then we take the derivative. Again, 1 to any exponent is 1, so the answer is 1/3. That's negative 2 over 9. How far am I taking this? To the third. So if I plug in 1, it's negative 2 over 9. One more time. So it's positive 10 over 27. And that'd be negative 8 over 3. So it's 10 over 27. Make sure I did that right. Good. And then what does the form, the pattern look like? So start with f at 1 is 1. They're not all positive value. The first two are positive. So then plus 1/3, and then the pattern. So this one's, because it's not 0, it's 1. So it's x minus 1 to the 1 over 1 factorial. Then the next one is negative 2 over 9. That's x minus 1 to the 2 over 2 factorial. The next one's 10 over 27. That's x minus 1 to the 3 over 3 factorial. And there it is. All right, number 6. Use the definition of a fourth degree centering the, so we have h at x equal ln x. And again, we're using 1, so it's a Taylor. So ln 1 is 0. The derivative of ln x is 1 over x. If I plug in 1, the answer is 1. The second derivative, think of this as x to the negative 1, so it's negative x to the negative 2. When I plug in 1, 1 to any exponent is 1, but it's a negative 1. Fourth degree, okay. Negative and a negative is positive 2. And then one more. So when I plug in 1, and be careful here, this is derivative, second derivative, third derivative, and then the fourth derivative. Sometimes you see the number 4. And those are the numbers I get. 0, 1, negative 1, 2, and negative 6. Perfect. And now the pattern. So we start with 0 plus 1, x minus 1 over 1 factorial. Then it's negative 1, x minus 1 to the 2 over 2 factorial. Then it's 2, x minus 1 to the 3 over 3 factorial. And then it's negative 6, x minus 1 to the 4 over 4 factorial. Done. Number 7. Use the polynomial from problem 6 to approximate ln 1.3. So then you would plug in 1.3 for x. And if you use your calculator, what answer do you get? But 0.261975. 8. Use the definition of a Taylor. So C equals pi over 4. And f at x equals sine x. So first of all, the y coordinate at pi over 4 is root 2 over 2. The derivative of sine is cosine, and the derivative there is the same answer, root 2 over 2. The second derivative is going to be negative sine. So if I plug in pi over 4, it's negative root 2 over 2. We'll stop at 4. The derivative of negative sine x is negative cosine x. So it's root 2 over 2, but it's negative root 2 over 2. And then it just starts all over again. So the derivative of negative cosine would be negative negative sine, which is positive sine, and so on. So what's the pattern here? So we start with root 2 over 2 plus root 2 over 2 x minus pi over 4 to the 1 over 1 factorial. Then the next pattern, now it's negative root 2 over 2 x minus pi over 4 to the 2 over 2 factorial. Now it's negative root 2 over 2 x minus pi over 4 to the 3 over 3 factorial, and so on. And then you'd follow that pattern and go back to the beginning again. Number 9. Use the definition of Taylor series. Show 4 terms, zeros don't count, and a general term. So if it's centered at 0, it's called a Maclaurin, but it's also a Taylor. So f at x equals cosine 2x. F at 0, if I plug in 0, cosine 0 is equal to 1. The derivative is sine, negative sine, 2x with a hook of 2. If I plug in 0, the value of sine at 0 is 0. Sine is cosine. The hook makes it negative 4. Plug in 0. you get 1, but it's negative 4 times 1. It'd be negative, but a negative times a negative is positive. The hook times 4 is 8. And this is 0. With a hook, this is going to be 16 cosine and then it's going to be negative 32 as it alternates. And this is the last one that gives us it. That's positive 64. Alright, so you have the values that you need. So I'm going to start with 1 plus, that's actually minus, so 1 minus, here, let's follow the pattern. 1 plus 0, x to the 1 over 1 factorial, minus 4x squared over 2 factorial, plus 0, x cubed over 3 factorial, plus 16 x to the 4th over 4 factorial, then 0, and then 64. 64 negative. So no, it's fine. And there you go. All right, number 10. Use the definition of a Maclaurin series. We have a function. Maclaurin means f at 0. So if I plug in 0, the derivative here, the bottom, or maybe we just write it as 1 plus x to the negative 1. So it would be negative 1 plus x to the negative 2. So then the derivative at 0, 1 to any exponent's 1, so it makes it negative 1. The second derivative, 1 plus x to the negative, well, negative times the negative makes it positive 2. This is negative 3. So the second derivative at 0 would be 2. Let's do it one more time. Then we got 1, 2, 3, 4. So negative 3 times 2 is negative 6. Subtract 1. So 1 to any exponent, so it's negative 6. Now the pattern, what we were trying to practice. So we start with 1 minus 1 x to the 1 over 1 factorial plus 2 x squared over 2 factorial minus 6 x3 over 3 factorial, and we did it. And honestly, this simplifies. The 1's divide out, the 2's divide out. 3 factorial is 6, so the 6's divide out. It ends up being x to the 1, x squared, x cubed, x to the 4th. Just alternates back and forth. Number 11. That was 11. That was 10. And 11 looks similar, because it is. Write a geometric series expansion for the same one. So to understand the series expansion, the first term, So first of all, we're going to write it as this, where a1 is the first term and the common ratio is negative x. That's the interval of convergence from -1 to 1. So the first term is 1. Then you multiply by negative x. Multiply, and so on. You actually, when you simplify it, it's the same answer. And so on. Number 12. So there's two ways to handle this. So 1 over x minus 1 is a geometric. And it needs to be in the form 1 subtract. So for that to be -1, and then the x to be positive, it would be 2 minus x, right? Yeah. And so our first term is 1, and the common ratio is 2 minus x. So we have 1, then multiply by 2 minus x, and then multiply by 2 minus x, and then multiply by 2 minus x, and you have the answer. You could also treat it as a Taylor, and you get the same answer if you simplified it, but I think that's easier. Use the series from problem 12 to find 4 terms in the general terms of the series expansion about x equals 2 for ln x minus 1. So for ln x minus 1, if you integrate 1 over x minus 1, that's what it equals. So the integration of 1 over x minus 1 equals ln x minus 1. So all I would need to do then is integrate each one. So integrate 1 and it's x. The next one would be 2 minus x, add 1 to the exponent and divide. The next one, oh, and it has a hook that makes it negative. The next one, you add 1 to the exponent and divide. Again, it has a hook that makes it negative. And then keep following that pattern. We're just integrating all along, following that pattern. Number 14. The Taylor series of function about x equals 3 is given. What is the value of the third derivative at 3? So I'm going to look at the third one. So that one, first derivative, second derivative, third derivative. So that means the answer is 7. Understanding the pattern. Number 50. Let f at x be a function. So f at 0 equals 2. The derivative at x is 3 times f at x. And the nth derivative is that. Give the first 4 terms. So we have that. The derivative at 0. So f at 0 is 2, so 3 times 2 is 6. The second derivative is 3 times the first derivative. That's what it's saying. So 3 times 6 is 18. All right, we're almost there. So the next one would be 3 times 18, which is 54. And then use these ones. So first of all, I start at 2, then 6, x to the 1 over 1 factorial, 18 x squared over 2 factorial, and then 54 x cubed over 3 factorial. Part B, find f at x by solving the differential equation. So f at x is just a fancy way of saying y. So dy by dx equals 3y. And then solve that with that initial condition of f at 0 equaling 2. So we have this. We're going to separate the variables. We're going to integrate it. And then we're going to write it exponentially. And we know plus or minus e to the c is just a constant. And then we're going to plug in 0, 2. So if you plug in 0, c2 is equal to 2. So we have 2e to the 3x. That's solving it. And it's done. Number 16. Turn the page. Let f be the function defined by this. And so on. I got it written down here. I think it says g at x. It says g prime at x equals f at x. I had black ink over it, so it made it tough to see. So if I integrate this, g at x equals the integration of f at x dx. It also says g at 0 equals 2. And then it says, what does g at x equal? So we're going to integrate this. And so on. So we just integrate each one. Number 17. The Taylor series for a function about x equals 0 equals that. Write the first 4 non-zero terms in the general term for the derivative. So the derivative of 4 over 3x is, well, 2 is 0. So it's just 4 over 3. That's 16 over 9. That's 48 over 27. And so on. Use the appropriate second degree Taylor polynomial approximation for f at 0.2 and the derivative at 0.2. So that means we're going to plug in 0.2. I'm just going to go this far. The further you go, the more accurate it is, but this is good enough for me. So you plug in 0.2, into here, the function, and then use your calculator, but I'll do it for you. And you get 2.302. For the derivative, you'd plug it into the derivative. So you have 4 over 3, 16 over 9.2, 48 over 27.2 squared. And again, you'd use your calculator, and you get 1.760 about. Part C says use the values found in Part B to approximate the equation of a tangent line at point 2. So x is 0.2, the y value is 2.302, and the slope is the derivative, which is about 1.760. So it would be y equals the slope, x minus 0.2 plus 2.302. 18. We're going to do up to 20, I think, for this video. So 18. You're given a Maclaurin series. What's the derivative at 0? So first of all, the derivative of 1 is 0. The derivative of 1x is 1, so it's 1 over that. The denominators are just going to stay the same when you do the derivative. So it'd be 1 over 2 factorial, which is 1/2. But the pattern, 2x over 3 factorial, 3x squared over 4 factorial, and so on. If I want to know what the derivative at 0 is, all of this is 0, whatever I can keep going. So the answer would just be 1/2. For part B, find the 15th derivative at 0. Trying to see how they did it. So the pattern would be the 15th derivative at 0 divided by 15 factorial, and then x to the 15. I'm not sure. I'm just going to give you the answer. I don't even know what, I'll be honest, in terms of what they did here to get the 15th. I have to think through it. But for right now, we're going to let it go and say the answer is 1 over 16. Think about it. All right, number 19. Find a geometric power series. All right, this one we can try to figure out. So it's 1 minus negative 4x squared. So it's in the right form. So the first term is x, and the common ratio is negative 4x squared. So the first term is x, and then multiply by negative 4x squared, and just keep doing that. Remember, you're adding the exponents as you do it, so on. Show 4 terms. I didn't do it. So again, negative 4 times that is negative 16x to the 7. The general term, in terms of what it would look like, if I started at 0 to infinity, first of all, it alternates. And then 4 to the n, x to the 2n plus 1 because it's odd. So if I plug in 0, it works. If I plug in 1, 2, 3, and so on, it works. And then this gives me the odd exponent for x. All right, number 20. Oh, and the interval of convergence would have to go between -1 and 1. So you divide by 4. That would change the arrow direction. And then you would square root. Oh, we could do it that way too. So the absolute value of 4x squared has to be less than 1. So that's just 4x squared has to be less than 1. Divide by 4. And then square root. Be positive or negative. There's your interval of convergence. All right. Here the common ratio is 3x. Divide by 3. That's the interval of convergence between -1/3 and +1/3. So the first term, when you plug in 0, is 4, and then it's 1 subtract 3x. So it's 4 over 1 subtract 3x. All right. We did good work. All right, we'll do part 2. We'll do the rest of the assignment. Mr. G. Math over and out. I'm super proud of you for doing your work, for not giving up and doing your best. Till next time.